Hello everybody, today we are starting our note on transformation of sinusoidal functions. So we're going to start with a chart, you'll see it at the front of your note, that just kind of refreshes what we know about how the different parameters affect a function. Okay, so if this seems like totally out there to you, go back to Unit 1 when we learned about transformations initially, and you can look at that video again or look at those notes. But I'm basically going to go through the transformations quite quickly and focus more on how it specifically changes sinusoidal functions. So you can go ahead and take a look at what A, K, D, and C, how they affect the graph. And I'm going to go ahead and tell you to just pause the video and copy these down because we've gone through them other times. So if you want them explained to you again, you can just look at another video, okay? All right, so now that you have these all copied down, we'll go through how each one affects specifically a sinusoidal function. So a vertical stretch, so taking it and going this way or compressing it this way, will affect the amplitude, the value of the amplitude. Okay, so whatever the A value is actually the absolute value of A is going to be equal to the amplitude, because normally the amplitude is 1. So if it's being vertically stretched by 3, now the vertical amplitude, or the amplitude, is 3, because it used to be 1. 3 times 1 is 3. Okay, if A is a half, the amplitude is now a half. So you can just look at the function, and whatever the A value is the amplitude. Okay, it also, you can think about it, it affects the max and the min as well, right? Because it'll affect how high those are above and below the axis. Okay, so K affects the period. So in fact, the period is going to be equal to 360 degrees divided by K. All right? So if K is greater than 1, then therefore that's a shorter period, right? Because it's being compressed. K is greater than 1. It's actually the absolute value of K. So if that's greater than 1, like 3, then that means everything is being compressed by a third. So therefore, instead of 360 degrees, we divide that by 3. Now we have a period of only 120 degrees. So our whole cycle will happen in 120 degrees instead of in 360 degrees. Another way to think about that is that there'll be 3 cycles in 360 degrees instead of just 1, because it's been compressed by 3. Okay? If K is between 0 and 1, the absolute value of K that is, then it's a longer period. Okay, so what about a K value of 1/5? That means it's a horizontal stretch by 5. So you'd multiply 360 by 5, because 360 divided by a fifth is the same as 360 times 5, right? So you'd multiply 360 by 5, and that's your period. Another way to think about it is that only a fifth of a period will now exist in the first 360 degrees. Okay, translating left to right, well, D is just equal to the phase shift. Okay, so it just kind of affects where everything is in left to right. So remember, if D is greater than 0, that would look like something like x minus 3, because it's always of the form x minus D. And D less than 0 would look like x plus 3, because that would be x minus a minus 3, okay? And the vertical translation up or down, the biggest thing is that C, whatever that C value is equal to the axis. Okay, so, or you can think about it, the equation of the axis, y equals C, is the equation of the axis. So that just moves everything up or down. So I really like this because these parameters have a direct effect right back onto the function. So you can just look at it and know what the axis is. You can just look at the function and know what the amplitude is. And from that, it's pretty easy to figure out the maximum and the minimum, and it's relatively easy to figure out the period when you know K. So I actually find graphing, you're gonna laugh at me, graphing sinusoidal functions rather relaxing, because it's just, if you get in the groove and you understand it, it's really quite straightforward, okay? It's just getting there to where you can do it. Obviously that's the difficult part, but once you get it for the most part, in my experience. Okay, so we're gonna start, oh, and then there's a bit on the bottom here. So remember to factor out K. Okay, the period of a sinusoidal function is 360 over K. That's a very important formula. And we're going to apply these. I often apply all of K, A, and C together at once, and then we do D. So then we shift. So what we're going to do first is a series of simple examples. So what I would suggest, you have this page of simple examples. Draw a sign on each of them, okay? One tick is 90 degrees. So you're gonna go up, middle, so start at 0, up, 0, down, 0. Okay, so do that for all 4, then you have those set up. Okay, the point of this is that we're comparing sine x to, here we're doing A, here we're doing K, then D, then C. Okay, just one at a time so that you understand each one individually before we combine them. Okay, I also suggest using color here to differentiate. So now we're going to do y equals 2 sine x. So this is a vertical stretch by a factor of 2. So all the y values are twice as high as they used to be. So therefore, 0 times 2 is just 0, it stays there. Now this is 1 high, so it's 1 times 2 is 2, so it's going to be 2 high. 0 stays there, so I should mark these as well. This will be twice as low, so down here. And this will remain the same because 0 times 2 is 0. So there you have it. There is a vertical stretch by a factor of 2. Okay? Now, we're going to do a vertical compression by a factor of 1/2. Okay? So, everything is half as high as it used to be. So 0 is 0. Instead of 1, we have a half. 0, 0. Instead of -1, we have -1/2. And 0, 0. Remember, we're referring to the original sine function, not the pink 2 sine x. So here we have it. So it's been vertically compressed. So there we go. Now I'm actually going to add one that's negative. So if we just have, let's say, y equals negative sine x. Okay? So then all of the y values are then reflected. So this would stay here, this would be down here, up here, this is up here, and this is back at 0. So that's what a reflection would look like. Okay? So that's how A affects the sine curve. Now we'll go with K. So K, you'll notice the difference of K is that it's within the argument of sine. So it's still multiplication, but it's inside the argument here. So we'll start with sine of 2x. So that means a sine of 2x means that your period is now 360 divided by K, so by 2. So a period is now 180 degrees. So you're going to get through the whole cycle in half the amount of space. So I like to think about this as like, okay, so I'm starting here and ending here. So in a sine curve, I always start at a minimum. I start on the axis, I end on the axis, and halfway through, I'm also at the axis. Okay, in a sine curve, I start on the axis, I end on the axis, and then halfway through, I'm always on the axis. Now between these two, if I haven't been reflected, it's at the maximum. And between these two, it's at the minimum. So that creates this curve. So, ooh, that was bad. Oh, sorry. Okay, Now you can also think about it that all these points have been compressed by a factor of a half. So they're all half as far out as they used to be. So instead of this being at 90, it's at 45. This was at 180, now it's at 90. This was at 270, now it's at 135. This was at 360, now it's at 180. Okay? So, oh, that should have been, I apologize, that should have been down at -1 though still. Okay, so there, it's the same height, it's just that it's squished in. So we can actually draw another period. So notice how I do this. This is how I prefer to do it. My beginning, my end, and my middle, and then halfway up between the first two, and down between the last two. So there we go. I have 2 cycles within the same amount of time. Okay? The period is 180. Okay? Now for sine of a half x, my period is now 360 divided by 2, divided by a half, which is the same as 360 divided by 2. So that's 720 degrees. So everything's twice as far out as it used to be. Okay, so my beginning is here. Now my middle is now at 360, and my end, I'm not even showing it. Okay, it doesn't even show up on this graph. So this one, instead of being 90 out, will be 180 out, this maximum. Okay, this axis, instead of being 180, it's now 360. Here, instead of being this, it's twice as far out. So 1, 2, 3, 4, 5, 6 grid squares. So I'm going to go another 6 grid squares. 1, 2, 3, 4, 5. So here's my minimum, and I don't even have room to show. So normally, if this was an assignment or something, you would make sure your graph is big enough, but I wanted to keep everything on one nice linear thing here. So there we go. So then its period is 720 degrees, so it only gets through half of its cycle within 360 degrees. So that's horizontally stretched. Okay? Now we'll do the translations. So it's the stretches and the compressions that determine the shape of the function. Okay, so how skinny or tall it is, or how short or fat it is. And it's the translations that determine where it is. I'm just going to get this right just a second. The translations that determine where it is on the plane. Okay, so the A and the K determine the shape, and then the D and the C determine, oh, this is tough, determine the location. To me, that's just a simpler way of thinking about it. Okay, there we go. Okay, no more using green. All right, so now we're going to do D and then C. So, purple. Okay, so our sine x I already drew. So this one, this first one of sine x minus 180, this is just move right 180 degrees, okay? Because D is equal to positive 180 when it's written this way, minus 180, okay? So you just translate them. This one, you move 180 degrees. This one, you move 180 degrees. So 180 degrees on this is represented by 1, 2, 3, 4 ticks, grid marks. So 1, 2. So this one now we move 1, 2, 3, 4. This one we move 1, 2, 3, 4. And this one we move 1, 2, 3, 4. Okay, so it's the same curve. It looks the exact same in terms of its shape. It's just shifted to the right by 180 degrees. So that's this one. Now I'll do plus 90. So in this case, D is equal to negative 90. So we're going left 90 degrees. So 90 degrees on my scale here is represented by 2 tick marks of the grid. So this goes 2 tick marks to minus 90. This 2 tick marks to 0. This 2 tick marks to 90. This guy 2 tick marks to 180. And this guy 2 tick marks to 270. So I'm just representing one cycle, okay? It would continue, but that's where it would go. So it's just moving left or right. Just left or right that way. The shape stays the same if all you have is a D value. Okay, similarly for C, the shape will stay the same. You're just moving up or down. So +1 just means you're moving everything up 1. Okay, so that's represented by 2 grid marks, tick marks on my grid. Okay, because this is 1. This is going up to 1. This is moving from 1 up to 2, from 0 to 1, from -1 to 0, and from 0 to 1. So there we go. Our nice sinusoidal curve just moved up. Okay? Then if I'm just moving, if I have a -1/2, this just means down by 0.5. So 0.5 on my scale is represented by 1 grid mark. So down 0.5, down 0.5, down 0.5, down 0.5, and down 0.5. And I draw a nice, smooth curve. So that's just been translated down. Okay, so I'm going to stop this video here. The next part of this note is more complicated examples where we are putting the parameters together and you're doing a whole bunch of translations at once. So I want to make sure that you completely master this note before you move on, and then it will be just so much fun. You'll have such nice, beautiful sinusoidal curves. It'll look great. Okay, thanks for watching. Hope you learned lots.